everybody. My name is Deepa. I work at the National Center for Biological Sciences in India, in Bangalore. And I'll do a little, spiel about this at the end, how you should all visit at some point. I'm going to tell you today about some surprising results we had from work with tribolium flower beetles, which we use in the lab to understand many different, or ask many different questions about the ecology and evolution of certain populations. And as with many sort of interesting questions in biology or in evolutionary biology, Darwin and Fisher have already thought about this and said a bunch about why sex ratios should evolve to be the way they are, and why are they balanced for many populations, and why do we think that any departures from this balanced sex ratio might be important for populations, how would they affect fitness of individuals. So in a nutshell, the major hypotheses for answering why altering sex ratio affects fitness have traditionally been ones that include some aspect of sexual attractions. So people think, and there's plenty of evidence for this, that there's intersexual conflict. So males and females have different strategies to maximize their fitness, and these may sometimes be at odds with each other. And if you have biased sex ratios that are skewed towards any one sex, this conflict is escalated, which then might result in reduced fitness for one or the other sex. Similarly, if you have intrasexual competition where different individuals, many times males, are competing for the same or a limited number of females, again, you have increased conflict between individuals, which can then result in female harm in many cases, and again, reduce female fitness. But I want to today talk about another aspect of sex ratios, which is the impact on non-sexual resource competition. So, as we all know, we not only need to find mates, but we also need to survive ourselves and our babies to survive. Right? So when we think of sex ratio, we often tend to ignore the impacts of sex ratios on resource competition. So to ask what actually happens in flower beetle groups, which are these cosmopolitan pest species, flower beetles typically have a balanced sex ratio, and we can rear them in the lab very easily. So we asked whether flower beetle populations are affected by changing group sex ratio, and if so, what is the mechanism underlying these effects. So the nice thing about flower beetles is they have the potential to show both sexual competition and resource competition. This is well known from many previous studies. So females and males will both male multiply. Females can store sperm for a really long time. So at least for most of their reproductive lifespan, females can utilize sperm from a single mating or mating in a few hours with a single male. And there's also male and female mate choice that is well understood. And finally, there's resource competition that is mediated by crowding. Right? So flower beetles live in, poop in, eat, reproduce in flower. And so if you put them in a box, basically this media gets really nasty and it gets efficient by crowding. And this limitation on food and oviposition space can then therefore have implications for their fitness. So it gives us the opportunity to test multiple hypotheses in a single system and ask what is the underlying basis for the observed effects of sex ratio. So I'm going to simplify a bigger study that we did to address this, focusing on 3 different treatments that we have for sex ratios. There's a male-biased treatment with one female and 3 males. There's an unbiased treatment with 3 of each, and a female-biased treatment with 3 females and a single male. And these are all housed in little petri dishes with flowers inside. And what we did is monitored the fitness of individual females pulled out from each of these groups across their lifespan. So what we're doing here is removing a female from a given group, putting her in isolation with fresh flower, having her lay eggs, and then asking how many of those eggs develop successfully into offspring after 3 weeks. Right? And as you can see, females that are pulled out from the male-biased groups consistently throughout their lifespan, throughout their reproductive lifespan, seem to have more offspring that they produce, which is kind of surprising because in most other insects where people have studied the impacts of sex ratio, people have found that if you increase the number of males in a population or in a group, perhaps due to male harassment, sometimes well understood because of male harassment, female fitness decreases. And we're seeing exactly the opposite result here, where unbiased and female biased groups impose much lower selection on females. And to figure out whether this is because of quality of eggs, which is changing, or quantity of eggs, we looked at how many eggs females were laying each time. And again, we find that male biased groups had females laying more eggs on average. So what they said is it's not that the females in female biased groups are laying poorer eggs, poorer quality eggs, they're just laying fewer eggs. So this was one of our first clues, and we should have really gotten the answer right here, but we didn't. So one of the things we wanted to test now is to really separate out whether sexual or other interactions are important for these witness effects. Let's take mated females that are focal females, mated to a single male, and expose them to flower which has been conditioned by either male biased or female biased groups before, and then measure their fecundity. And what this lets us do is ask, well, is there something about the flower that changes because they're known to chemically communicate a lot, or are physical interactions necessary and important to see the observed witness? What we find is that regardless of how long individuals are exposed to this conditioned flower, so different colors and shades here just say, are they exposed for 6 hours or 2 days or 1 day? In each case, you find that females are still laying fewer eggs when they're exposed to flower, which has been previously used by female biased groups. So what this suggests strongly is that interactions with males or other females are not important, and there's some chemical communication perhaps that's mediated through the flower, which is the key for understanding these results. So we further tried to say, well, are the females important or are the males important? So again, we used flower that was conditioned by either male or female versions. And we find that female fitness is again reduced, or fecundity is reduced, when they're exposed to female conditioned flower. So again, the males sort of seem to drop out of the picture eventually. And there's very nice old work that had been done showing that paired sting glands that tribolium beetles have in the thorax and in the abdomen secrete these chemicals, including quinones, which are thought to reduce or suppress fecundity of females. So there's previous work which was done a while ago that didn't sort of really tease apart this relationship, and there were experimental difficulties that they had. So what we could do is that we could dissect out the sting glands and then expose focal females to either sting glands from male beetles or female beetles, and when females were exposed to female sting glands, their fecundity dropped again, suggesting, okay, fine, there's something about the sting glands which is important, but what is it? So previous chemical ecology work has shown that there are 2 major sting gland components which might be the culprits here. So there's ethyl and methyl benzoquinone. The chemicals are simple benzene ring, and this methyl group here can be replaced by an ethyl group instead. So it's a very small change, and there's 2 of these chemicals. Thankfully, one of them, which is methyl benzoquinone, you can buy from SEMA. Ethyl, which is EBQ, you can't. So we had colleagues who are chemists and who do this stuff, sort of synthesizes for us, which was fantastic. And then we could test whether exposing your naive beetles to EBQ or MBQ then reduces their fecundity. And what we see is that relative to controls which are exposed to only the solvent, females that are exposed to ethyl benzoquinone are laying fewer eggs. So then we know that it's EBQ which is playing this major role. What's an interesting aside, which I'm not going to show you today, is it seems that MBQ seems to have antimicrobial properties, and people have again known this for sting glands in general, that those secretions do have antimicrobial properties. So what seems to be happening is that 2 different components of the same sting gland have evolved to perform different functions, and we're now looking at how these 2 concentrations are related, or is there a trade-off, and so on. But for now, getting back to the EBQ story, the final thing to do was to show that if you have groups that are female biased versus male biased, do they actually produce more EBQ? And this is preliminary data from HPLC, which shows that indeed, in female biased groups, females are secreting much more EBQ than others. Right? So what seems to be happening then is that all the females in female biased groups are suppressing each other's fecundity through this chemical secretion, whereas other in male biased groups, they're not getting as much quinone, and therefore the fecundity is not suppressed. And it was really fun to find old data from Mike Wade, who had done some other experiments for something entirely different. And when we reanalyze these data, we find that the proportion of females in a group, as the number of offspring per female, it decreases as the proportion of females in the group changes. And there's a density effect, which is well known and understood in tribalism, which you see. But it's really nice that in an independent study, you see the same result come up for a much larger series of sex ratios than what we were able to test. And Mike was also kind enough to dig up some 30-year-old notebooks from his office and send me more data that he never published, and that also shows a parallel trend. So it's very, very good to know that. And so just to summarize, I think it's female interference competition that's determining fitness, and there's a relatively minor role for males. And this is really just a byproduct or an outcome of regular old density dependence regulation in these populations. And I finally want to end by saying that female competition may actually often underlie such fitness effects of sex ratio. So there's previous studies showing that in mosquito fish, fitness decreases with female density, but not with male harassment. So he was able, Chad Smith was the first operator, was able to independently manipulate both of these, and he was able to show that its male harassment does not have an impact on mosquito fish fitness. And there's, of course, many studies from mammals and social insects showing that in groups of females, dominant females will suppress reproduction of other females, right? So this is not entirely unknown, and perhaps what we need to do is look at all of these different effects of sex ratios together to really understand how sex ratios might evolve and maybe maintained in natural populations. I'd like to end by acknowledging people who were critical for this work. So it was is a postdoc in my lab who's been driving this work. Radhika is the chemist. She's a faculty at SPS who recently joined, and I don't think without her we could have done these experiments as nicely. And then all of these are various rotation students and technicians who help with the work. And I want to end also by finally saying that write to me if you'd like to visit us. We have a fantastic campus, many faculty working on aspects of ecology and evolution. Bangalore is a nice place. So yeah, if you're interested, write to me.
Do the offspring of the females at the different sex ratios differ in any other ways? I'm imagining that maybe what's happening is fewer higher quality offspring that are more competitive.
Yeah, so the data that I showed you on number of offspring is actually adult offspring that are produced. And so as far as I can tell, they're not different in their function. So we didn't really count how many offspring they had afterwards. But based on the numbers that I do see at that point, it doesn't look like there's a big difference.
Is it that the females are actually producing more of these compounds when they're together, or simply that the total amount is increasing because each one is producing the same amount?
Yeah, no, so it's per capita increase, per capita secretion, which does increase. So what we measured is we had this thing called sea light, which is an absorbent material in which we put the virus. And then we look at how much, but then divided by 3 to sort of account for that. Yeah.
Is acting as a deterrent so that females that are migrating around could encounter these high rates and know that they shouldn't be laying eggs and move away?
I think you're asking about dispersal after, as a result.
Yeah, well, just females moving around. If they encounter an area where there were females already, they don't.
Yeah, quite likely. Yeah, that's possible. Okay, I think it's time for the next.